This is Professor Z. Welcome back to Math in the Real World. Today we're going to pretend we're wildlife biologists and we're examining the population growth of two species, the coyote and the deer. Both of these species started with a population of 3. The coyote had a nice steady increase in numbers. But what we noticed is that the elk population exploded. Perhaps this is due to the loss of natural predators in the wild. We're not sure, but let's take a look at these numbers and see if we can come up with some mathematical models and make some predictions about the future. In order to make this comparison, we're going to start at year 0 for both animals and a population of 3. So that means the X, or the input, represents the time in years, and the output is the number of animals. We recorded this population growth over 4 years. When we increase the year by 1, the population has a steady increase of 2 each year. We call that constant increase a common difference. Perhaps you can even guess the equation. You got it. It's a linear function. In a linear function, the coefficient of x, or the slope, is your common difference. And the constant term, the b, is your starting value. So for our example, that would be y equals 2x plus 3. We can test out our equation by simply plugging in the x values from our model and seeing if they match the output of y. This would be a good time to pause the video and see if you can do that yourself. A linear function is a straight line, of course. As x increases, y will increase by the same amount each time. In our example, years is on the x-axis, the number of coyotes is on the y-axis. Now about that crazy elk population, this time we noticed that as the year increased by 1, the population doubled. Every year it just doubled. It kept doubling. So many deer. What's happening here? We call this a common multiplier. Each year, the amount is 2 times the year before. 6 is 2 times 3, and 12 is 2 times 6, but 6 is 3 times 2, and 24 is 12 times 2, but 12... Oh, hold on a minute. Let's take this a little slower. After 7 years, our population should be 3 times 2 times 2 times 2 times 2 times 2 times 2 times 2. Can you guess the equation here? You're right. This is an exponential function. Y equals a times b raised to some exponent. What exactly do all those variables represent anyway? Let's take a closer look. The b is your common multiplier, and the a is your starting value. In our model, that gives us y equals 3 times 2 to the power x. Again, x represents the number of years, and y represents the number of deer. Again, you can test your model by plugging in the values from the chart and seeing if the input matches the output. This is another good time to pause the video and see if you can do that yourself. When you graph this function, you're going to have years on the x-axis and the number of deer on the y-axis. The population increases faster and faster and faster, giving you an exponential function. It's a beautiful curve. Okay, to sum it up, our linear function had a constant rate of change, a common difference. We added the same number each year to the population. But the exponential function had a common multiplier. For each year, we multiplied the population by the same number. In our models, the population didn't seem too much different at first, the first couple of years. But after time, you'll notice that exponential function grows faster and faster and faster. As a matter of fact, an exponential function will always surpass a linear function in the long run. Thanks for joining me. I hope you come back again. See you next time. Don't forget, math is good.